So welcome everyone to our OpenSim webinar. My name is Jen Hicks. I'm the OpenSim R&D Manager and the Associate Director of our National Center for Simulation and Rehab Research, and I'll be serving as the moderator for today's webinar. I'm pleased to welcome today's presenter, John Mortensen and Calvin Kuo. They'll be presenting a muscle and ligament model of the head and neck to study physiological motions and dynamic impacts. Next slide. So OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating movements of human and animals. So the goal of our webinar series is to showcase the cutting-edge research that's being performed with the OpenSim software. OpenSim is also a large and geographically diverse community of users. So the second goal of our webinar series is to provide a platform so that members of the OpenSim community can communicate with each other and form new collaborations. Next slide. Before we get started, a couple quick reminders about the format of the webinar. We definitely want to answer your questions, but we'll do that at the end of the presentation using the WebEx Q&A panel. If you need additional technical help, you can consult the guide on our website. Next slide. So now I'd like to go ahead and introduce our speakers. So Calvin Kuo is currently a Killam postdoctoral scholar at the University of British Columbia in the departments of kinesiology and computer science, where he's modeling neural sensory integration for motion perception and applying wearable IMUs to study human motion outside of the lab. Calvin worked in the robotics section at the Jet Propulsion Laboratory and then obtained his MS and PhD from Stanford University under the co-supervision of professors David Camarillo and Scott Delp in 2018. And then John Mortensen is currently a PhD candidate at the University of Utah in the Ergonomics and Safety Lab, where he's modeling the effects of active neck muscle during impacts in American football. John obtained his MS from the University of Utah and will be defending his dissertation in the next few weeks. That's exciting. John's PhD committee includes Professor Andrew Merriweather from the University of Utah and Professor Anita Vasavada from Washington State University, who developed the original OpenSim neck model on which the models discussed in this webinar are based. So the models being discussed today in the webinar were developed as part of John and Calvin's PhD work. And with that, I will let you guys take it away. Really looking forward to your talk.
All right, thank you. So to start off, I'd like to...
And you'll need to make sure you unmute your mic because we don't hear you yet. Oh.
Are we good?
Yes, now I can hear you too.
Awesome. All right. Well, before we dive in, I wanted to pose the question of what good OpenSim head and neck models are. Right? What do we want to use them for? There are plenty of finite element models of the head and neck out there that have been used for things like car crashes or injury tolerance loads. You can get a lot more detailed information. But with OpenSim head and neck models, there's lots of different applications that are really available to us. And some of these applications include ergonomic studies. For those of you tuning in, some of you may look more like the model on the left here, that you're leaning too close to your computer screen, or some of you may look more like the model on the right, where you're leaning too far away, both of which are not very good postures for your neck. And using a model that is readily able to predict muscle forces and joint loads, such as the OpenSim models can really give us some insight for different ergonomic studies. You can also imagine how realistic models of the head and neck can be used for rehabilitation or analysis of disease, because these OpenSim models allow us to replicate motions we observe and capture through motion capture, and we can quite easily investigate the effects of altering muscle capabilities or muscle activation patterns to understand these different diseases and what interventions might be helpful. And then as more of a topic for the discussion today, we can do impact simulations. We can simulate slips and falls onto compliant flooring where we have some active neck muscles, and we can investigate how well they reduce impact velocity. Or for car crashes or things like American football, we can look at the effect of active neck muscles during impacts to the head. So if they're bracing for impact, how does that change things? And that's really our motivation here, is that we can use OpenSim models for these different applications and are able to do thousands of simulations rather easily, with being able to change different parameters in the model quickly. So that's a real benefit of having these head and neck models. However, there's some real challenges with developing these head and neck models, and predominantly those challenges are accurately modeling forces on the head. We need to have realistic muscle forces so that you can have physiological motions, that your model should be able to replicate motions you observe experimentally. Otherwise, you can't really use your model to do these ergonomic studies or impact studies, because you're not generating the correct moments from the active muscle. And another problem is developing correct passive tissue forces, that when you apply a measured external force, we need to be able to recreate those in OpenSim and see the same head rotation as a result of that force. So to give you an idea of how crucial these improvements that Calvin and I have been working on are, we included this animation, which will show a fairly low magnitude impact to the head with muscle forces and without passive structures that Calvin and I have been working on. You apply the force, and we see this catastrophic failure that is clearly not realistic and not very useful. And so today you'll be hearing first from me, and I'll be talking about the development of the Hyoid model, which is the name of the OpenSim model that my group published about a year ago, and how we were able to develop realistic neck strength and reproduce functional movements. And then after I'm done talking, we'll hear from Calvin, who will talk more about his passive tissue model and developing cervical ligaments in the model, and also those what that means for impact simulations. So to get started, I'm going to talk about the development of the Hyoid model, which was driven by two real needs. We wanted to be able to reproduce experimental moment generation, so we want to be able to produce these realistic strengths in the neck in all directions. And we think that the best way to prove that we can do that is to recreate these experimental setups. That's what this picture is here, where the model is attempting to apply force to what would be a load cell in an experimental setup. And then, as we showed before, we really wanted to be able to simulate these physiological motions, be able to do motions that we see without the need for large reserve actuators. So the starting point was a model that's known as the Massey Model. It was developed by Cazzola and published in 2017. And this model was very useful. It is a huge step forward from what we had. It is a full body model, as you can see, with ideal actuators at each of the joints, except for the neck, which was developed to include musculature. And so there were added inertial properties to the 1998 Vasavada model, which all the models are based on today. And also was included a really impressive custom scapular-clavicular joint, which made it possible to use this model for rugby simulations to look at loading in the neck and possible modes of failure during rugby scrums. However, one of the limitations that was stated was that the flexion strength was roughly 1/3 of experimental data. So the model was only able to do 30% of what it needed to in flexion. And this is highlighted a little more by the fact that they had to scale flexor and extensor muscle group strengths by different factors. And they chose to do this, but to match extension and lateral bending strength, because if they were to match flexion strength, the scaling factors would be unrealistically large and provide a lot of passive stiffness from the neck. And so with this as a starting point, I thought, well, if we use this same approach and just scale muscle strengths differently, maybe we could get realistic strengths in all directions. So I did a really simple optimization problem in which I allowed the optimizer to alter the strength of each muscle in the model by a factor from 0 to 10, with the objective of matching realistic strength in flexion, extension, lateral bending, and axial rotation. But this couldn't be done. The best it could do, even with letting some muscles be 10 times stronger than they should, was still really quite far off, as you can see in this table on the left. And let's look at why that is. If here we have the head and neck model with only the primary flexor muscle shown, the sternocleidomastoid muscle. And the kinematic constraints that were developed by Vasavada that for these models make it so that the lower cervical spine and the upper cervical spine are constrained to move as functions of the rotation of the head, which means that you have 6 degrees of freedom, 3 in the lower cervical spine and 3 in the upper. If you look at the where these green dots represent where the center of rotation are for the upper and lower cervical spine, you can see that the primary flexor muscle will produce flexion in the lower cervical spine, but part of the muscle will cause extension in the upper cervical spine. And this problem is made worse if the model goes into any sort of extension at all. Now most of this muscle is providing only extension in the upper cervical spine. So it's really a problem of the geometry of the existing muscles that no matter how strong they are, what configuration you get, you'll get problems that you won't be able to match up both flexion and lateral bending strength because of where these muscles attach. So that leaves us with either changing the muscle attachment points or changing kinematic constraints, or looking at muscles that were not included in the original model. And so that's where we started. We looked at what are known as hyoid muscles. And these are the muscles that run on the front of your throat, and they raise and lower the hyoid bone, which is a bone that sort of floats under your jaw here and assists with swallowing, and has been proposed by a few studies that it could act as a fairly significant flexor muscle. And so that was our hypothesis, that if we included this hyoid muscle, we'd really be able to get this realistic strength in all directions. So we added hyoid muscles using position data and physical cross-sectional area data from available literature. And we started using the original muscle strengths defined by Vasavada and multiplied the physical cross-sectional area of these hyoid muscles by 35 newtons for every centimeter squared of physical cross-sectional area, which was the same multiplier that Dr. Vasavada used when she developed this model. And then we assumed that the infrahyoid muscles, the ones that are below the hyoid bone, move with the C3 vertebrae, and the suprahyoid muscles move with C1, which is a limitation we'll be talking about a little bit more as we go on. But then once these hyoid muscles were added, we wanted to simulate actual experiments, as I was mentioning earlier. This video shows you what flexion and extension looks like in the lower cervical spine, and then what flexion and extension look like in the upper cervical spine. And a real possible way of calculating your strength of your model incorrectly is to only look at the moment that the muscles can generate in the lower cervical spine or the upper cervical spine. If you look at them separately, you're going to artificially raise the flexion strength because, as we noted, these muscles can cause extension in the upper cervical spine, really lowering how effective the muscle is at bringing the whole neck into flexion. So we thought dynamic simulations of actual experiments are necessary. So here we have a setup where the torso is constrained, and this would be a subject that is strapped down to a chair wearing a helmet with a load cell attached to it, with the subject told to flex their muscles as hard as they can. And then we were able to compare how effective the model was at resisting the measured forces that were seen in different experimental studies. So if you do that, you find that the Massey model does really well in extension, and that's because all the muscles are modeled up really well. However, it does fairly poorly in the other directions because it doesn't have that stability that the hyoid muscle offers in the upper cervical spine, or that lack of flexion. Once we add those hyoid muscles in there, the forces get better, but they still require scaling similar to the Massey model. So there's still this flexion moment inconsistency that for some reason we have to scale the flexor muscles as stronger for physical cross-sectional area than they do for the extensor muscles. And I'll talk more about that. But once we do that, we can get values that match up with experimental data really well. So we're able to reproduce these strengths, which is something that we haven't been able to do until we added these hyoid muscles. And as for functional movements, for those of you who are new to OpenSim, reserve actuators are these imaginary forces that we add to the model that help the model to recreate movements that we observe through motion capture. And so they kick in when the muscles are not strong enough to produce the motions that we see. And so you can understand that if you need a lot of force from these reserve actuators, you can't trust that your model is reproducing these movements very well. And so this graph here shows the reserve actuators from the Massey model and also the Hyoid model without any scaling, and then with some scaling to work on that flexion moment inconsistency problem we talked about. And it's used for a motion that goes through just flexion and extension. You can see that the Massey model does really well when the model is going just through extension. But when it goes through flexion, it needs these reserve actuators, especially for both the upper and cervical spine. And the Hyoid model without any scaling still requires some reserve actuators, but once we do this scaling, the reserve actuators are virtually zero, meaning that this scaled Hyoid model can reproduce these physiological motions quite well. So talking about that flexion moment inconsistency, there really is no reason to suspect that flexor muscles are stronger than extensor muscles. So there has to be some other way we can improve this model. We looked at a few different things. One thing we looked at was shifting the center of rotation of the vertebrae, so changing the kinematic constraints. And we found that if you shifted these center of rotations posteriorly by 5.5 millimeters, you can get this equal scaling factor so that you can assume each muscle has the same strength for equal physical cross-sectional area. However, the literature suggests that you're only allowed to shift this by a maximum of 1.1 millimeters to still be within 95% confidence of what is realistic. So we know we can't shift it that far. And then another thing we thought about was maybe during these experimental setups that posture of the subject was not perfectly neutral. And we found that if you put the model into 15 degrees of flexion, you'll see an increase in flexion strength and a decrease in extension strength, which gets us closer to having this realistic scaling factors, but still not all the way there. So there's still, and this is still an open problem that is not only a problem for OpenSim models, but also for finite element models, that several models really struggle to have muscle forces based on physical cross-sectional area and get this realistic flexion strength. Some other possibilities we haven't looked into yet are wide muscles. OpenSim struggles to represent these wide muscles fairly well. That's why you saw with the sternocleidomastoid muscle that it was split into multiple muscle segments. That's really supposed to be one muscle, but because of how OpenSim is modeled, they have to be these lines that can't function together. Another problem is that this model doesn't include any muscle wrapping with other muscles, so that muscles are free to pass through each other in extreme postures, which clearly isn't realistic. And also, we didn't look at the possibility of raising the shoulders. When you're doing maximum flexion, perhaps you're raising the shoulders and changing moment arm of these flexion muscles. And we'll do a quick demo where we'll explore this hyoid model, and I'll talk about the limitation I mentioned earlier with the hyoid bone, and I'll also show you some results from doing computed muscle control of a physiological motion. So right here we have this hyoid model, which you can download on SimTK's website, and you can get this folder here from the page that we have up. And right here I'm showing you the hyoid scaled model, which is the model I would suggest using unless you're trying to get at this moment flexion consistency problem. Then you should use the original hyoid, the unscaled hyoid model, which has strengths based off of Vasavada's original model. So you can see here, I can show you what the different kinematics look like, that you can see motion in the lower cervical spine. These are the 3 degrees of freedom of the lower cervical spine, and then you got 3 degrees of freedom in the upper cervical spine. So looking just at the hyoid muscles that we added, you can see that these infrahyoid muscles move with the lower cervical spine really well. But if you move just the upper cervical spine, you see that the suprahyoid muscles can move independently. And so there's all these muscles are supposed to be attaching to the same bone, and this is a problem that we need to focus on in the future. But if we look at a model that was made subject specific by scaling to experimental data, we can see what it looks like. This model changes size a little bit, and then running computed muscle control, you can do these physiological motions in which you can see how muscle forces are changing as the model goes through different motions. These are simple to run, and all this data and for various physiological motions are available on SimTK's website. With that, I think we are about ready to move on to the second portion of this webinar, in which Calvin will take over. So I pass the screen over to him.
All right, thanks, John. So now that John has walked through the addition of the hyoid flexor muscles to the model, I'm going to discuss the addition of passive ligaments to the cervical spine. While the hyoid flexor muscles provide additional flexion moment to the head and neck for physiological movements, we found that the additional flexion moment was still not enough to stabilize the head following impacts to the front of the head. Indeed, the muscles on their own are too weak to stabilize following impacts in any direction. Thus, we sought to include accurate ligament structures to provide additional stabilizing moments. Ligaments on their own have been studied extensively in the literature, and the material properties of the cervical spine ligaments specifically have been reported from cadaveric samples. Ligaments have a characteristic nonlinear force length curve that looks something like this. Ligaments in their neutral state are comprised of collagen fibers that are somewhat tangled and twisted, but as the ligament is initially stretched, these fibers are straightened, giving a characteristic toe region in the force displacement graph. Once the collagen fibers are straightened, the ligament experiences a relatively linear elastic region as collagen fibers are stretched elastically. As the ligament is stretched further, some collagen fibers begin to fail, leading to plastic deformation, and eventually the entire ligament fails. Cervical spine ligaments in particular have also been tested at drastically different lengthening rates, as it is thought that ligaments undergo up to 1,000 strain per second in impact scenarios such as whiplash. Shown here is an example of the stress-strain curve for the alar ligament under a quasi-static loading condition of 0.005 strain per second and a highly dynamic loading condition of nearly 2,000 strain per second. The linear region in the quasi-static condition has a relatively low Young's modulus, whereas the linear region of the dynamic condition has a substantially larger Young's modulus. The lengthening rate dependence of the ligament material properties is typically represented with the Young's modulus E scaling with the log of the lengthening rate. Thus, we introduced a new rate-dependent ligament in OpenSim that incorporates both a force length and force velocity component. Notice this mirrors closely the hill-type muscle models with the force length and force velocity curves. For the force length relationship, we used a piecewise linear function to represent the major toe region and linear elastic regions of the ligament force length curve. For the force velocity relationship, we used a single slope right here that scales the ligament force with respect to the log of the lengthening rate or velocity. The force velocity relationship also assumes that the force scaling is unity in quasi-static loading regimes. The material properties for the cervical spine ligaments were all obtained from previous literature on cadaveric samples spanning the last 3 decades. The ligaments were placed based on anatomical definitions obtained from literature. To validate our ligament geometry and material properties, we performed a series of validation simulations on vertebral functional units. Briefly, a vertebral functional unit consists of a single intervertebral joint or consecutive vertebra with the ligament and structure and disc intact. With these functional units, we rotated the superior vertebra with respect to the inferior vertebra about the primary anatomical axes, sagittal flexion extension, coronolateral flexion, and axial rotation. This resulted in moments generated by the ligaments that were stretched from neutral, from which we generated moment displacement curves. These curves were compared to previous literature on cadaveric samples tested in a similar manner. An example validation of the C5-C6 functional unit is shown here, compared against two previous studies. Because we modeled ligaments individually in our model, we could not only compute the total moments produced by these ligaments as one might achieve with OpenSim bushings, which are effectively torsional springs, but we could also compute the contribution from individual ligaments. As an example from this video, the annulus fibrosus fibers on the anterior side of the intervertebral disc provide the largest flexion moment in this particular functional unit. With the individual functional units validated, we subsequently implemented the ligaments into the full cervical spine model, as you can see here. Shown here is the full ligament structure added to John's musculoskeletal model. The ligaments currently only extend down to the first thoracic vertebra, though in reality, many of the cervical spine ligaments are continuous with the respective counterparts in the thoracic spine. Now, with the ligaments implemented to provide additional passive moments, we simulated experimental mild head impacts that we collected previously by applying experimental impact forces and comparing simulation kinematics to measured kinematics. In these experiments, we had subjects wear a headpiece through which impact loads of approximately 200 newtons were applied. These loads were measured with an inline tension meter, and we measured the head kinematics using high-rate inertial measurement units. We had subjects maintain upright posture prior to impact by either minimally activating neck muscles, which we considered relaxed, or by maximally activating neck muscles, which we considered a muscle co-contraction condition. We measured muscle activity with EMG on the sternocleidomastoid muscles. We ran forward simulations of our head and neck model scaled to subject mass, neck length, and isometric strength, and compared the resulting rotational and linear kinematics of the head to the IMU measures. Shown here in the graphs are the comparison of head angular velocity and acceleration from the model in red to the corresponding subject kinematics. The blue represents the average response over 3 trials for this particular subject, while the gray represents the boundary. So in the spirit of open source dissemination and fostering collaboration, we've made a lot of the material covered here available on SimTK. Raw, de-identified experimental data is provided, such as IMU kinematics and impact forces, which are necessary to run and validate forward dynamic simulations. Note that we cannot include video here, as this includes identifiable information. We've also included John's model with the added rate-dependent ligament structure, along with a custom Python scaling function that is necessary to properly scale the ligaments. We've also included all of the experimental models, simulations, and results files. Now, this model that we've posted has a few key differences other than the addition of ligaments when compared with John's model. First, we actually decoupled the individual intervertebral joints, which results in our model having many more degrees of freedom. As John mentioned, the cervical spine curvature in previous iterations of this OpenSim model were achieved by coupling the rotation of individual intervertebral joints to 3 or 6 independent degrees of freedom. We decoupled our intervertebral joints with the intention of supporting simulations of axial loads, where it is known that the cervical spine can buckle. The downside of this is that it makes this model very difficult to use with the static optimization and compute muscle control functions in OpenSim, which are tools that determine muscle forces from measured motion. Thus, we believe the ideal use case for this particular model is in a forward dynamics analysis, where we apply forces and observe and simulate the motion out. Now, briefly, I'd like to demonstrate how to load the rate-dependent ligament into the OpenSim environment, as it is a custom .dll model, and also where the ligament states live, so you can pull things like ligament force or ligament length for future analysis. So the first thing you'll want to do is go to your home drive, in my case the C drive, and find the OpenSim folder. Once in the OpenSim folder, you can look at the look for the plugins folder, and for me right now it's empty. If you download our model from SimTK, you'll find there's the model here, and also this DLL file that represents the custom ligament. Go ahead and copy that DLL file into the plugins folder, and now you can boot up OpenSim. And give it a moment here. Okay, now that OpenSim is open, if you want to load the custom ligament, you'll go to Tools, Scroll down to user plugins, and you can see that the DLL file is present. If you click on that, it'll load in the DLL file. Once loaded, you can now open the custom head and neck model that we have provided, and you can double check that the ligaments are present by hiding the muscles. And you should be able to see the ligament structure here, as we've noticed before. Now, if you run a forward dynamic simulation with this model, the ligament states aren't actually stored in the normal states file. Actually, what you want to do to pull out the states information from the ligaments is run the forward dynamics with a force reporter analysis tool, which reports forces that are produced by any force-producing structure inside the simulation. So I'm going to pull up an example of a force reporter file here. And you can see in this force reporter file, all of the ligaments have their states loaded here. So in this case, the anterior longitudinal ligament on the spine has force, strain, length, strain rate, and strain rate states, which you can find in this particular file. Okay, so now that I've gone through how the rate-dependent ligament model works, I'd like to show a few analyses and results that we've performed using this model. From the impact simulations that we performed, we were able to compute the relative moment contribution to head stabilization during these impact from the muscles and the ligaments separately. This is an example of angular acceleration profile that shows a clean acceleration phase when the head is impacted and accelerated into motion. This is followed immediately by a deceleration phase where the neck soft tissue structures are stabilizing the head back to rest. With these phases defined, we computed the moments and angular impulses produced by the external force, muscles, and ligaments during the acceleration and deceleration phases of our impacts. What we found from our simulations first was that the impact indeed was applied almost entirely during the acceleration phase, which implies that the impact causes the acceleration. Second was that when subjects relaxed their neck muscles, shown here in the graph in the center, the ligaments were the primary contributors to the stabilizing moment, providing larger moments than the passive component of the hill-type models, muscle models, which are shown in blue. Note that the positive impulses here represent impulses that accelerate the head, and negative impulses are impulses that contribute to deceleration. Furthermore, as one might expect, we also found that the active musculature was the primary contributor to stabilizing moments when subjects co-contracted their neck muscles, shown here in red. In a separate study run by some of my undergraduate students, we wanted to investigate how ligament sprains affected head and neck stability. We represented these sprains as a tear in the ligament, which means we simply removed the corresponding element in the OpenSim model. We then applied fixed moments in the primary anatomical axes with lateral bending shown here, and observed how much the head rotated from upright. What we found in these simulations was that the loss of lower cervical spine ligaments, such as the intertransverse ligament at the C7-C6 level, resulted in greater head deflections. I like to show this example as it demonstrates how quickly and effectively the OpenSim models can be in performing parametric style analysis that John alluded to earlier, particularly when compared with finite element models. While possibly not as fidelic as finite element models, these types of analyses in OpenSim can quickly narrow down parameter spaces for further refined analysis with finite element models. While we have primarily used the rate ligament models to study direct impacts, we could extend the model to simulate whiplash injuries in automotive impacts or cervical spine buckling in axial loads. The rate-dependent ligament can also be extended to model important ligaments throughout the body, such as the knee and ankle or the lumbar and thoracic spine. In conclusion, oh, sorry, John, I think this is you.
All right, can you hear me?
Yeah.
All right, so with the hyoid bone motion, if you could play that again, Calvin, or play that so that you can remember what we were talking about. That we need to be able to define the hyoid bone because the suprahyoid and infrahyoid muscles should be moving together. So future work should define a function that describes hyoid bone motion, and this is a difficult problem because it should be based on posture alone, or should it include active muscles as well in defining where this floating bone should be at any given time. So that is a subject of future work that can be done with X-ray studies or MRIs and motion. Then the next one. And also, muscle activation patterns. If you're bracing for impact, you're going to do two things. You're going to change your posture, and you're also going to have co-activation of neck muscles, which is opposing muscle groups activating, which provide no net moment. So bracing and stiffening up your neck through active muscles. Computed muscle control and static optimization, they are defined by minimizing total muscle activation for these well-learned movements, which works pretty well, but it avoids co-activation, so they can't be used in this situation of bracing for impact. So we can look at different objective functions besides minimizing total muscle activation, such as maximizing activation, maximizing force, or as we developed here at the University of Utah, maximizing applied moment. You will, in the near future, we'll be releasing a tool which allows, which is a collection of MATLAB scripts, which allows you to look at these different objective functions and different effects they have on muscle activation patterns and what that could mean for bracing for impact.
So in conclusion, John and I have presented our work on improving the force and moment production capabilities of the OpenSim head and neck model. John, in his development of the hyoid model, has implemented hyoid muscles that produce realistic neck strength in all directions to reproduce functional movements. In adding rate-dependent cervical spine ligaments, I've included passive structures that provide additional stability in head impact that allow for simulations of real-world impacts. Both of our models can be found on our respective SimTK pages, along with some other useful information. Before we close, we would like to thank Jen Hicks, Joy Koo, and Scott Delp for inviting us to give this webinar and organizing the logistics. And we'd also like to thank Professor Anita Vasavada and Professor Dario Cazzola's group for developing the original musculoskeletal models upon which our models are based. We hope that this model will continue to evolve and improve, as you can see here, and be used in future studies. So with that, I think we'll conclude.
Okay, can you hear me okay? All right. Thank you guys for a really great talk. That was super interesting work. Now we'll go ahead and open up the webinar for questions. So we'll take your questions. There'll be text-based, so find the Q&A box in your WebEx system and type in your question and make sure you select to ask all panelists so we can see those questions come in. So we have one question that came in already from Jonathan Walter. And his question, would adding degrees of freedom at all of the individual cervical vertebrae, I assume, change the dynamic moment arms of the extensor muscles when the neck is extended?
All right, I can answer that. That's a really good question, and one that would be fairly difficult to simulate because with motion capture or observing what people's postures are when they're doing these maximum voluntary contractions, it's really difficult to get a feel for what each vertebrae is doing without doing some sort of X-ray or fluoroscopic or MRI imaging as well. So if we did all those, we could be able to get a more realistic posture of the neck that would change these moment arms of the extensor muscles and the flexor muscles. But it'd be very difficult to use for physiological simulations. As well, getting stability in the neck for these maximum voluntary contractions would be difficult without making sure we have very well-defined ligaments, as well as the really deep cervical muscles, which help stabilize the neck. That's one thing that the kinematic constraints do, is they help stabilize the neck as well for these functional movements.
Okay, great. Thank you, John. So if others have questions, go ahead and type those in the Q&A panel. I'll ask a question. This is for Calvin. I'm sorry if I missed the details, but so you were doing forward dynamic simulations. Can you talk a little bit more about how you drove those simulations? It did look like your validation results were pretty good when you compared the simulated to the experimental kinematics. Did that require much tuning of parameters, or is that how it kind of worked out of the box?
Yeah, sure. So thanks for the question. So We basically, the first thing we did was we actually scaled all of our subject specific models to subject height, let me think, height, mass, and isometric strength. So we measured our subject isometric strength in flexion and lateral flexion, which were the two primary, modes that we wanted to test. So we impacted these folks in extension and lateral flexion. And then we actually, during these impacts, had measurements of the applied force through our inline tension meter, which was applied roughly through the center of mass of the head. So we applied an external load force to the OpenSim model through that point. One thing that we did do was we actually restricted the torso of the OpenSim model. So we fixed it to ground. In our experiments, we had subjects sitting in sort of a rigid back chair and strapped in order to try and minimize that torso motion. Although this is a limitation, as there is never perfectly zero motion. And the other thing that we did do for the muscle activation was that we used our EMG measurements of the sternocleidomastoid to sort of inform the amount of activation in the muscles pre-impact, and we held that activation constant. So for the relaxed case, we used the sternocleidomastoid activation to sort of solve for the muscle activations that maintain an upright posture while minimizing the activation of the remainder muscles. And the flip side, for the co-contracted case, we maximized the activation of the remainder muscles. And then once we did that, we applied the loads and observed the kinematics. And we didn't have to do any specific tuning outside of scaling the subject parameters to get the results that we did.
Great, thank you. That makes a lot of sense. Now we have a question from Nicholas Gomez. Calvin, you mentioned that the individual vertebrae were decoupled. Were their motions purely constrained by the implemented ligaments, or were those bodies still connected?
So those bodies were still connected. We decoupled the rotational kinematic degrees of freedom. So basically, each intervertebral joint has the full 3 degree of freedom rotational kinematics, except for the upper cervical spine, which is a little bit special in our model. But the linear degrees of freedom are still fixed. So each intervertebral joint doesn't have the translational degrees of freedom, only the rotational.
Okay. Now a question from Anita Vasavada. She says, beautiful work, John and Calvin. Calvin, you mentioned a Python scaling function for the ligament model. Is that for scaling to subject size?
Yeah, so for us, we had some trouble. So the scaling function, I think, in OpenSim scales the muscles and the skeletal structure nicely. But since the ligament is a custom model, we had some trouble running the scaling tool as is to scale the ligaments themselves. So the scaling tool is primarily for scaling the geometry of the ligament, but you can also scale the stiffnesses of the ligaments as well with that particular Python code.
Okay. So now a question from Loe Al-Salehi. So this is a question more about how you might use the models that you guys developed for other purposes. So is there a way to simulate the effect of muscle activation in the neck on the alignment or posture of the cervical spine?
Well, it depends on what you mean by that. If you're trying to see how different muscle activation changes the curvature of the spine without changing sort of the rotation of the head, that'd be a little more difficult. It might be possible with the decoupled kinematic constraints that are in Calvin's model. But if instead you're just meaning predicting muscle forces based on different postures or different inputs to the head, yes, that is very simple to do using computed muscle control or static optimization.
Okay, and a follow-on to that was, is it possible to include a boundary condition like gravity, for example, to simulate an inverted posture?
Absolutely, gravity is included with the OpenSim models themselves, and you can turn that on and off and change, if you wanted to, how strong the gravity is, but not often you do that.
Right. Or you can, simulate have gravity be present and simulate an inverted posture as well.
Yes.
By changing the orientation of the model. Okay, she says thank you. I think that did indeed answer her question. If there aren't any further questions, we'll go ahead and wrap up the webinar. I think there's another slide or two if you guys could click through. Thank you everyone for the great discussion and the great questions. Next slide. You can find out more information about the National Center for Simulation and Rehab Research and other resources for the OpenSim community on our website. And we also want to definitely acknowledge our funding sources, including an NIH grant that funds our NCSRR. Next slide. So there's the link to our website. We also ask that you fill out the survey that will appear in the pop-up window at the conclusion of the webinar, which will help us improve our webinar series and choose topics for upcoming webinars. You'll also get a follow-up email that will have a link to the recording of the webinar and also a link to the SimTK projects that John and Calvin pointed out. So thank you again for participating. Thank you again, John and Calvin, for the great webinar. We hope everyone will continue to stay involved with OpenSim. Bye-bye. Thank you.
Yeah, thank you.
Thank you.